So it's good that we have an atmosphere, but given what we said about the creation of Earth, one can ask, where did it come from? When the Earth formed, it was forming out of silicates and aluminum and calcium. I didn't say anything about water. Some amount of water can be trapped in minerals, we know. And I didn't say anything about gases. Earth was too small a planet to trap hydrogen and helium, which were the only gases plentiful. And indeed, when Earth formed, it would have had a very tenuous atmosphere, if any. But when you cook rocks, Earth formed, it was very hot. The rocks on the surface were cooked, and they released carbon dioxide and nitrogen that can be trapped in minerals and is released when you heat them. This gave us the beginnings of an atmosphere of nitrogen and mostly carbon dioxide. Much more was released when the cooking rocks on the interior of Earth, in the mantle, were available by volcanic action, and so this releases gases from the interior of the planet, and we get a burgeoning atmosphere of carbon dioxide. Where water came from, well, there's some water, as I said, trapped in the rocks, but calculations show that that probably would not have been enough to create the oceans that we see on Earth today, and what there was of water would have been baked out and lost to space early in Earth's history. So it is imagined that most of the water that forms our oceans was in fact imported from farther out in the solar system in the form of ice, where it formed in the form of ice, and then fell in and impacted Earth during that heavy bombardment period 3.8, 3.9 billion years ago. And so the fact that we have water is the result of import. And water creates a dynamic. Water falls as ice on the surface of Earth. It boils off. It accumulates as water vapor in the atmosphere. It condenses and creates the oceans that we see. And the rain that falls from the atmosphere when the water condenses dissolves carbon dioxide, which is then dissolved in the ocean and is fixed in sediments. This process is accelerated by the emergence of continents about 3.5 billion years ago, and the amount of carbon dioxide in the atmosphere is gradually removed, leaving us with an atmosphere of nitrogen. That's 3/4 of the atmosphere already there with traces of water vapor. We need oxygen. The other quarter, free oxygen on Earth, is produced by the beginnings of plant life, actually. Initially, this goes to oxidize sediments of iron and sulfur, but eventually, as these are fully oxidized, free oxygen begins to exist in the Earth's atmosphere, starting about 700 million years ago, and the level of oxygen approaches the 20% that we comfortably breathe today. This is therefore the atmosphere both enables the existence of life and is shaped by the existence of life. All the oxygen we breathe was produced locally in photosynthetic processes. So this is something about the chemistry of the atmosphere. What does the physics tell us about the atmosphere? Well, the atmosphere, like the mantle, is a convective system. It's heated from below because the ground is warmer than the atmosphere, so air down close to the ground is heated by conduction through the atmosphere, from the ground, and then we have a fluid which is being heated from below. This drives convection patterns. The differential heating shapes where the convection cells are going to fall. So globally, Earth has on each hemisphere these 3 large convection cells. Hot air rises near the equator. Cooler air sinks at mid-latitudes, and then there's one more instance of hot air rising at upper latitudes, and of course at the poles cold air is sinking. And so we build these 3 convection cells. This drives northerly or southerly surface winds, and by the way, explains the properties of trade winds. This, along with the Earth's rotation, explains trade winds because it's a property of something called the Coriolis effect, that inertial objects in the northern hemisphere are always appear to be deflected to the right, and inertial objects in the southern hemisphere always appear to be deflected to the left. Like many great discoveries, this was first found out in the process of developing weaponry by artillery people. And so what this tells us is that near the equator, with the southerly winds in the north turning right and the northerly winds in the south turning left, we have these winds that blow from east to west. and at mid-latitudes we have these winds that blow west to east, and in between is a region known to sailors as the doldrums, where there are no global trade winds, and sailboats had trouble moving themselves. And this explains lots of properties of Earth's climate and weather that we won't have time or need to discuss, but this global pattern of circulation cells will repeat and be generic, and so we should enjoy what we can of the physics of it. So we've talked about the Earth's surface, we've talked about the Earth's interior. The Earth doesn't stop at the atmosphere, which tapers off into interplanetary space. There's one important property of Earth that extends way beyond the extent of the atmosphere, and this is the Earth's magnetic field. As anybody who's used a compass knows, Earth is a magnet. Earth is a magnet whose poles roughly align with the axis of rotation. In fact, the Earth's south magnetic pole is roughly aligned with the Earth's north geographic pole. This is just a matter of convention. We call north pole of a magnet the part that faces north. Since opposite poles of a magnet attract, this means that it's being attracted to the Earth's south magnetic pole. So here's a picture of the Earth's magnetic fields. The fields, remember, start at the north magnetic pole and enter into the south magnetic pole. And what this picture suggests to us, other than that the south pole is in the north, is that the source of the magnet is in the Earth's core. This is indeed true. The process by which the Earth's core generates a magnetic field is a non-trivial one. It's called a geodynamo, and it has to do with the confluence of three factors. One is that the core is being heated from within by the hotter inner core. So we have a liquid, metal-rich outer core full of conducting elements like iron and nickel. It's being heated from below, which drives convection. Along with the rotation of the Earth, this drives this convective flow and leads to an instability that generates a spontaneous magnetic field. It's not a trivial problem. It's not one that I'm going to write the equations for, but it's true that it's a understood phenomenon that rotation along with convection leads to spontaneous magnetic field, and that this field will roughly align itself with the axis of rotation. What is not true is that the South Pole needs to be at the Earth's geographic North Pole, and indeed, the geologic record shows that it hasn't always been that way. The field reverses polarity in a rather unpredictable way, on average every 500,000 years, and here's a sort of geologic record of the Earth's polarity. Regions that are in black indicate a polarity regions in white indicate a polarity the same as the current polarity. Regions in black indicate the opposite polarity. And you see that the intervals are somewhat random. There are long periods of stability, periods of rapid change. We're now in a relatively stable period, but there are indications that the Earth's magnetic field might change. Here is a sort of simulation of the Earth's magnetic field lines, including the complicated structure near the core, and here's what the field looks like during polarity change. As I said, the process is complicated. So the Earth is a magnet. This allows us to use magnetic compasses. What else does the field do for us? Why am I making such a big deal? The next demo might help us understand this. The interaction of charged particles and magnetic fields will come up again and again in this class, so this apparatus will allow us to study it. Inside that glass bulb is that shiny horizontal metal structure. That's an electron gun. When I turn on a current, there is a piece of metal there that will be heated, will emit electrons. Those will be accelerated, and the electron gun will emit horizontal beam of electrons into the bulb. Now, the bulb is nearly evacuated, so those electrons will be able to propagate rather freely, but there's a very tenuous atmosphere of some inert gas in there, and this means that when the electrons hit the gas, they will ionize the gas will glow, and we'll be able to trace where the electrons are going. Surrounding the bulb are these big coils. When I turn a current on through the coils, then as we saw last week's discussion of magnetism, we'll create a magnetic field penetrating the coils. So in the view we're seeing, that magnetic field will be directed from where we are sitting into the black backdrop. And we'll see what that does to the motion of the charged particles. Remember that moving charges are affected by magnetic fields. So here we've dimmed the light, we've turned on the electron beam, we see a nice straight electron beam, and we see that it ionizes the atoms of the gas, and the gas glows, so we can trace the position of the beam. And now I'm going to turn on the magnetic field, which in this image points from right to left. And we see that when the beam impinges upon the electrons, the straight electron beam is curled into this helical shape. And as I turn up the current in the coils, increasing the magnetic field, the helix tightens more and more. We see what happens after the electrons hit the bulb. The beam is absorbed. But by increasing the intensity of the beam, I can tighten the helix, make the radius with which the electrons move smaller. In other words, increasing their acceleration. Since their speed is pretty much constant, I weaken the field and the helix opens up. This is clearer perhaps in this view. We're viewing it from the side. The beam is moving to the right, and when I turn on the magnetic field, which now points away from us, I see a circle, which is the projection of the helix. When I tilt it, you see there's still a helix going on, but viewed from the side, it looks like a circle, and the radius of the circle is smaller when I make the magnetic field strong, and as I turn the magnetic field down, the radius of the circle grows. So now we understand what the magnetic field can do for us besides director compasses. What the magnetic field does is that it interacts with that solar wind of charged particles that are constantly being emitted by the sun. And what happens to these charged particles when they hit the Earth's magnetic field is that they go into circular motion in a direction perpendicular to the field. And essentially that means that they are trapped along the field lines. They can slide along the field lines. And rather than penetrate through the field and impinge upon the Earth, they are trapped along the field lines. And they travel along the field lines, sort of spiraling around them in the helices that we saw. And the next calculation that I couldn't show you with that demo shows that regions of strong magnetic field actually repel the particles. What that means is that if you look at the field lines, the particles impinging from the sun are trapped along the field lines. They propagate along the field lines until near the poles where the field intensifies. They are repelled, they bounce back, so they end up bouncing back and forth and creating the so-called Van Allen radiation belts. These are regions around the Earth where the magnetic field has trapped particles from the solar wind. And this prevents this intense flux of charged particles from impinging upon the Earth. Now, the solar wind actually implies a pressure to this. We often talk about charged particles. We saw what a magnetic field does to charged particles. Charged particles, in turn, influence a magnetic field when they're moving. We saw that, for example, with our electrons, which were moving in a circle. They themselves constituted a motion of charges in circles, which would generate a magnetic field. And as you can predict from stability, that magnetic field actually opposes the magnetic field in the coils that cause them to move in the helix. What that means is that when you have a magnetic field that is trapping a flux of charged particles, the momentum of those charged particles is absorbed by the magnetic field and essentially pushes it. You can imagine sort of a hydrodynamics problem where the charged particles are just pushing on the fields, and we'll often apply this sort of picture where the particles push on the field. What this shows you is what the Earth's magnetosphere actually looks like. The Earth is trying to make that nice apple-shaped, symmetric magnetic field, but the sun here on the left is pushing that field out so that the field is compressed on the left-hand side and then extends way off to the right. And this is the deformed magnetosphere. And what we see is that the flux from the sun is not constant. In the course of a magnetic storm, there's a dynamics here. And when the magnetic storm, when the stream of particles from the sun has enough flux, then some of them break through the atmosphere. And they break through the atmosphere where the magnetic field lines enter the atmosphere. That would be near the Earth's poles, and then they impinge upon the gases in Earth's atmosphere, and as they did in the tube, they ionize them, and this gives rise to the beautiful light show we call the aurora, in this case the aurora australis over Antarctica. So the charged particles get trapped along the field lines. When they penetrate, they enter the atmosphere along the field lines, which enter the atmosphere near the poles, and that is why we have auroras near the poles, and this is why the intensity of northern or southern lights is dependent upon the intensity of solar activity, as we will see next week. So let's summarize what Earth has taught us. We learned how to identify the benchmarks of tectonics. Look for those ridge-like structures, those linear mountain structures. Geological activity will be reflected in volcanoes. We learned the importance of an atmosphere and what that does to the temperature structure. We learned how to compute the equilibrium temperature of a planet about a star. And we learned that the existence of a solid and a liquid core of conducting material generates a magnetic field, which allows protection, leads to protection from the solar wind. This will become very important. And the last thing we learned is that the Earth's crust is very young. So as a way to test our understanding of the very early solar system, Earth is a poor place to do the study because the atmospherics, the erosion, geologic, tectonic activity erases the past rather quickly on Earth. Maybe we can find a better place to study that.